the AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, and welcome to today's session. My name is Andrea Manara from the ITU, the International Telecommunication Union. And it is an honor for me to introduce the last of 5 final events for this second edition of the ITU GeoAI Challenge. The ITU GeoAI Challenge aims to provide a platform for collaboratively addressing real-world geospatial problems by applying artificial intelligence machine learning to advance the United Nations Sustainable Development Goals. Participation is open to any individual from one of the 193 member states of the ITU. ITU provides also a state-of-the-art free-of-charge computing platform to participants of the challenge who do not have adequate access to computing resources in their respective institution. Today's session deals with the Hyperview Challenge on estimating soil parameters from hyperspectral images. We had 207 participants enrolled in the competition, and 62 active participants submitted solutions on the Zindi platform. The top 3 teams were invited for today's session to showcase their solution, and they will be awarded during this session for recognition of their outstanding performances. The Hyperview Challenge was originally developed as part of the IEEE International Conference on Image Processing 2022 conference, and has been revitalized for the ITU GeoAI Challenge 2023. The goal of this challenge is to use machine learning to advance the state-of-the-art for soil parameter retrieval from hyperspectral data in view of the Intuition 1 mission, which is the Intuition is a satellite mission designed by KP Labs to observe the Earth using an hyperspectral instrumental and an onboard computing unit which is able to process data using artificial intelligence in orbit. The challenge is curated by ESA F-lab together with the KP Labs and partner QZ Solution. Now it's my pleasure to introduce the host of this problem statement. Jakub, hello, and Nicolas. Jakub received his PhD and Doctor of Science degree from the Silesian University of Technology in Gliwice, Poland, where he's now an associate professor. He's also the head of artificial intelligence at KP Labs, where he shapes the scientific and industrial AI objectives of the company. He has been instrumental in designing the onboard deep learning capability of Intuition-1 and has contributed to other missions. His research interests include deep learning, hyperspectral data analysis, signal processing, remote sensing, and tackling practical challenges that arise in Earth observation to deploy scalable solution. And he was the general chair of the Hyperview Challenge at 2022 IEEE International Conference on Image Processing, and he's a senior member of IEEE. Nicolas Longuepé received his PhD from the University of Rennes in France, and then spent 3 years in the Earth Observation Research Center of the Japan Aerospace Exploration Agency. And then he spent 10 years at CLS France as a research engineer in the Radar Application Division. He's now working since September 2020 at the F-lab Explore Office at ESA in Italy, where he's particularly involved in the development of innovative Earth observation missions where artificial intelligence is directly deployed at the edge. His main scientific interests include SAR remote sensing and digital technologies such as machine learning, and he has been working on development of innovative SAR-based application for environmental and natural management and for maritime security. I will now give the floor to Jacob and Nicolas for their introduction to the competition and to brief us on the status of the Intuition-1 mission. Afterwards, we will have a 10 minutes presentation from each of the selected competitors before the announcement of the awards. Jacob and Nicolas, the floor is yours.
Thank you very much, Andrea. Okay, let me share my screen. Here you are. Can you confirm you see it?
Yes.
Okay, perfect. Thanks a lot, Andrea. Yeah, it's a pleasure to be here with Jacob from Capilabs to give you an overview of a little bit of what we are doing at ESA and also at Capilabs. So I'm Nicolas Longuepé, I'm an Earth observation data scientist there. So here we'll talk about Earth observations, because while taking the pulse of our planet, as you may know, is very important. I mean, we are facing many crises, environmental crises, climate change, and so on and so forth. So having this large-scale capabilities from satellite is something that I think is very crucial to really be able to have some informed decision after that. So at ESA, we are taking the pulse of planet via different satellites. As you may know, we have we are empowered by the European Commission to build the Copernicus satellites, and this is the Sentinel satellite that you can see here. You have the Sentinel-1, which is a synthetic aperture radar mission, Sentinel-2, which is a multispectrals. You have also some more dedicated mission like the Sentinel-3, which are looking at the ocean, for instance. Sentinel-5P is looking at the atmospheres and the pollutions. And in the coming years, we launch many more satellites for the European Commissions. In addition to that, we are working as well with the EUMETSAT so that we can provide them satellites that can observe key variables that help to predict the weather. And then on the other side, which are more on the science perspective, we are building as well at ESA some different missions that help to address some specific science aspects. So this is the portfolio of satellite that we are building more on the science part. And you have Gauche that measure the gravity. We have SMOS that measure the salinity and the water. Salinity, soil moisture as well. CryoSat monitoring the ice sheet and the sea ice. Swarm was about the magnetic fields. There have been aeolus that measure the 3D aspect of the wind. The cloud, the aerosol, the radiations is something that was measured by EarthScarce. This slide is not up to date. Biomass will be launched hopefully next year, and will measure actually the above ground biomass stored and in the trunk of forest, tropical forest mostly, and then also we'll look as well at fluorescence. So you see that with this satellite, I mean, we have the generic one from the Copernicus missions, but we have also a set of very specific, narrow and scientific oriented satellites here on these slides. So at the Ph-lab observation program directorate at ESA, and more specifically at the Ph-lab. So the Ph-lab is kind of disruptive lab. So we really cover the full pipeline for innovation. So we start from very blue sky ideas like TRL 1, even 0, I would say, and we go and help actually any companies to enter the market. So we cover the full pipeline for innovation. We're about 30 people working at the Ph-lab. Most of the guys are research fellows, so working on this low TRL stuff, but also we have staff working on more mature product and so on. We work mostly on what we call transformative or disruptive technology. We're not looking at interesting at incremental technologies. I mean, and here you see on the bottom on the right our definition for this transformative or disruptive technology. So we want to take the latest of the technological progress and also be really impactful in terms of science, but also in the market and in our ecosystems. AI is obviously one of the main components that we are looking after now. I mean, AI disrupting the society, as you may have seen lately, I don't know, with ChatGPT or any fancy AI model. So the idea of our mandate is really to take the latest of the technologies from the Google, Meta, Facebook, and so on, and try to foster the adoption within the Earth observation community. Because we believe that AI is a great tool to get really some insight from the Earth observation amount of data that we get from the different satellites. And it's not only ESA satellite, but also this information comes from different sources. It could be from social media, it could be from in situ, it could be from drones, whatsoever. So the idea of AI is really to ingest those massive amount of heterogeneous data and get some insight about our blue planet Earth. So this is our mandate, and this is what we are pushing. And I think now I will, if I'm not mistaken, I will pass the floor to Jacob, the colleague from Capilabs, that will detail a little bit what they have been doing lately, and also what exactly was this Hyperview challenge. Over to you, Jacob.
Yeah, thank you. So it's a big pleasure to be here. And as Nicola and Andrea mentioned, I'm heading an AI department at Capilabs. And as the Capilabs, we've been around for a couple of years already, 2016-ish. We are currently more than 80 people on board. And we are based in Poland, south of Poland, Gliwice, which is pretty close to Krakow. And we are currently looking at, a couple of different aspects of real missions. And our vision is to be the leader in autonomous systems. And to actually make this happen, we need to build upon our technological pillars, which we'll see in the next slide. Yeah, so we are, working to make sure that we have all the components that are necessary to build a real life mission, and it concerns software, hardware, and obviously AI for processing the raw data that we capture on board the satellite. Because as Nicola already mentioned, capturing raw data is cool, but I think even cooler is to extract some insights from the raw data that might be actionable and might be of use for the end user. And obviously the end users might be different, but at the end of the day, we are interested in getting the insights from the raw data that we could capture in orbit, because based on that, we know that we have a very huge scalability of different solutions for instance, Earth observation. And it's not only about image, we also work on signal processing, where we want to extract the parts of telemetry, which is the signals that are being captured by satellite, to understand if the satellite is working correctly or not. Because if we spot something which is abnormal, we could potentially take some actions faster to make sure that we can respond to such abnormal events that are happening on board the satellite. So we built upon software, hardware, AI, and we are trying to bring all things together to make sure that we could build something that is working in real life. So if we get to the next slide, we'll see the smart mission ecosystem, which basically summarizes all things that we do in a pretty nice way. We also work on our DPUs, so the data processing units that would allow us to process that raw data in orbit. And we have a family of different hardware pieces that could be used on both different missions. And of interest would be Leopard, which we'll see in a second. But also what I think worth mentioning is that we built the software and AI tools and libraries to make sure that we could easily tackle new challenges based on satellite data. So we also have the HERT, which is the library of different AI solutions for different downstream applications. And one of the downstream applications is soil analysis, and this is a very good example on where we could indeed bring impact in real life. So maybe we could get to the next one, where we'll start summarizing our Intuition-1 mission. That is something that, again, Andra and Nicola already mentioned. We built our own satellite, which was a super huge project for a couple of years. And there are a couple of interesting things about this satellite. First, we have the optical payload, which basically has the hyperspectral imager, meaning that we can capture a lot of bands which are separate but continuous for a given area of the Earth that we are observing. That means that we have much more potential information than we could have, for instance, in an RGB image, and we could exploit this information for quite an array of different downstream tasks. Again, soil analysis is just one example, but it is certainly much more than that. And on top of that, we have onboard processing, because we want to avoid downlinking huge amounts of raw data. We want to take action on board to make sure that we understand what is being captured, what are the insights from the raw data, and how we can respond to those insights. And to make this happen, we use Leopard, which is our DPU that is capable of running both classic and deep machine learning in orbit. Based on that, we can just compress the data to take action based on insights, not raw data. And maybe getting to the next one, we can see the goals of the entire mission. The primary goal was to prove the technology. So we want to verify the technology in orbit to see and to prove that Leopard and onboard processing could work in real life in an extreme environment. We are in orbit, so this is not on the ground processing. This is much more challenging to run things on board and to make sure that they work correctly. And the secondary goal, which is of interest for all of you guys, is that we wanted to have a real use case for processing data in orbit. And this soil mapping is a very good example where we could benefit from hyperspectral data. And this was the idea on building the HyperView challenge as well, and I'll talk about that in a second. As I mentioned, this is already in orbit, so we have Intuition-1 in there, and now we are in the sort of the commissioning phase to make sure that all things work properly, and we are slowly but surely getting to the point where we could capture the real data, process this real data using machine learning to extract some soil parameters, the soil parameters that you were also focusing in the challenge. I think interesting is that Leopard is already working, so we confirm that in orbit. And then we are getting into the HyperView as such. So we're pondering how to exploit the hyperspectral data for an important use case and for an important problem that could bring impact. And given a lot of spectral information, we're looking at the soil management, because we know that this is an extensive process, and it might be very cost inefficient and time consuming to sample soil on the ground, analyze it, and take action. So we wanted to build something that would also allow us to have better farming, because if we have better soil, then we directly impact farming. And again, if we have better farming, then we can get to better crops, because this is a direct impact of farming to get better crops, better quality, perhaps better quantity as well. And finally, if we manage soil properly, we could end up having better planets. So this is the chain of impact that we could bring to the table if we do onboard processing in a correct way to analyze all that we have in orbit. And then we designed the Hyperview challenge. As you all know, we are looking at 4 parameters of the soil that are of interest for the end user, for instance, for the farmers. And we want to make this totally non-invasive, meaning that we have the images and we want to extract those parameters from the image, which might capture a lot more area than we could do on the ground because of the sampling process. So that was the idea, to build a challenge, and to make this happen, we actually gathered the data together with our partners from curated Solutions. We got the hyperspectral images and also the in situ measurements of the soil. So we had the acquisition campaign in Poland. We gathered the hyperspectral images, we pre-processed them. So at the end of the day, you got the images that were already pre-processed. We had 150 bands, as you know. So we, sort of shrinked the data that we had to have 150 bands from which you were extracting the parameters using your algorithms of different kinds. And then we had the in-situ measurements. So we sampled soil on the ground, we mixed them together, sent to the lab, and we got the ground truth information about the parameters directly from the lab. So we have synchronized images and in-situ measurements, and based on that, we could build the ground truth data that you have. And also we have some unseen test data that was used for quantifying your generalization over the unseen patches. So the goal was to build a solution that could work in practice, that could automate the process of extracting the soil parameters, which are important for better farming and for making sure that we manage the soil properly and accurately. And that was your task for the Hyperview challenge.
So Andrea, I guess it's conclude our parts, and I guess we can switch now to the different pitches.
Excellent. Yes. Thank you very much, Nicolas and Jacob, for this very, very nice introduction. Very, very interesting, really very interesting project. So let's now go to the competitors. So I would like first to call Julius. If you can, hello, Julius, if you can share your screen and make your presentation. You have 10 minutes.
Thank you so much, Andrea. I hope you can all see my screen and hear me clearly.
Yeah, we see. Go ahead.
Okay. Thank you. So I'll start. First of all, thank you to ITU for organizing and facilitating this wonderful competition. So thank you, Nicola and Jakub, for the good work you are doing. This is an amazing project, and it was my first working with hyperspectral images, and it sounds very interesting. And I'm happy to be at this point where we are doing our presentation. So my name is Julius, and I'm a graduate student pursuing data analytics. My interests are in financial markets. I work in financial markets, that is research mostly. And my interests are in time series and other observation. And I'm currently ranked 5th on the platform. So I'll go straight to the introduction. So Nicola and Jakub explained it very well, that the project is a collaborative project between K-Lab and E-Lab. And they are looking for solutions that may transform or bring a revolution in agriculture by combining Earth observation with AI technologies. So yeah, so the concerns are that the traditional in situ soil analysis through sampling methods, they are very laborious and very inefficient, limiting scalability and also hindering timely access to crucial soil data for optimal fertilization by farmers. So this project focus was to address this need so that we may have more efficient and scalable solutions by harnessing the potential of advanced hyperspectral imaging from satellites and in-orbit AI processing. So the trained dataset consisted of some 1,732 hyperspectral image patches, while the test had around 1,154. So each image corresponded to an individual agricultural field. So these patches were varying in size and averaging around 60 by 60 pixels, all encoding crucial information with 150 contiguous hyperspectral bands for soil property prediction. So the ground truth labels, they represented soil parameters, and there were 4. That is phosphorus, potassium, magnesium, and soil acidity, pH. They were also provided alongside the training sample. So there's a picture there, and I think you already taken through by the team. So I will not talk a lot there. So my approach is I customized my training set with, we had been given a starter notebook. So I just customized a little, added some data augmentation, that is random cropping of the images, adding some noise for larger agricultural fields when loading the data sets. That was for the training. So after loading the data, I went ahead and tried to create a few more features. That is singular value decomposition, SVD, which captured spatial relationships. The wavelet transforms, which provided insights into local variations. Gradient calculations captured data changes, and fast Fourier transform, which revealed frequency domain characteristics. So these features were then concatenated. The spectral curve filtering was created for compact representation. So I did some data reshaping, that is trying to melt and merge here and there to ensure that they were compatible with the machine learning models that I used. I didn't go to deep learning, but I used the three models, light GBM and hist gradient boosting. So I tracked, of course, I tracked the root mean squared error for track how the models performed. And again, I only used default parameters for each of the model, meaning there was no hyperparameter tuning, which is something that maybe can be improved in future. So, but the reason was the data set had many features, which may have taken a lot of time to train. I was working on my local compute. We didn't have a lot of compute power. So my final submission for the challenge was an average of 2 models. That is the light GBM and the hist gradient boosting. And that one got an error of 0.269 on the Zindi platform. So I used a 5-fold k-fold splitting so that I could track my errors, my root mean squared error on my local computer. So, and I got interested to see how the various the 2 models performed in various soil parameters. So and you can see the table there for phosphorus. I think for all soil parameters, light GBM seemed to perform better than the hist gradient, slightly better. And so you can see the RMC values for phosphorus around 16 for both models, for potassium around 35, for magnesium around 20, and for soil acidity around 0.13 to 114, around there. So basically that was how the models performed. So the results on Zindi leaderboard were normalized. So Zindi divided the reference file by the starter code submission file to normalize the score. So what we have on the leaderboard could be a little different from what you have on my local compute because of the normalization. So I scaled my submission so that it was in line with the Zindi normalized values. At the beginning, I had not read the instruction that they had normalized, so I was getting very huge errors, and I was wondering how people are hacking good scores. Later on, just to be careful with the information page, I got to realize they had normalized their score. So that was what I did, and the outcomes were that the light GBM in the public leaderboard around an error of 0.265. And when the private leaderboard was revealed around 0.27. The history gradient you can also see around the same values. Yeah, and then I applied an average of the two results, the results from light GBM and the history gradient. I averaged the two, that is 50%, 50%. And yeah, so I was able to increase the accuracy a little bit to around 0.26. So that is all about the results. And then the conclusion is the additional features that I added, they moved my score from around 0.3 on the leaderboard to around 0.26, which was a good boost. Actually, I could have done more, maybe in future work, try to check on what more features can be added, because that one improves performance. So, and then I also faced a challenge with compute power. So high compute power could help do more augmentations, definitely, and create even more interesting features for further improvement. So for this challenge, I only applied free gold GPU for the task of getting or preparing my data. Yeah, so I also realized that his gradient benefited from selecting most important features, while light GPM did not. So that is something I did for his gradient, just trying to take the most important features and disregarding the ones that are not. Yes, so I still feel that deep learning could improve the results further, which is something I really wanted to explore, but I couldn't manage. Maybe next time I will manage that step. Yes, so that is my brief presentation for today's session. Thank you for listening.
Thank you very much. And now I'd like to invite Jacob to present. Hello, Jacob. We cannot hear you.
Good afternoon. Can you see my screen?
Okay, we can hear you now, and we can see your screen. Okay, go ahead.
Thank you very much. Yes.
In fact, we have an issue.
Good afternoon.
We cannot hear you well, Jacob.
Okay, thank you. Good afternoon. So I'll be presenting on the GeoAI challenge, estimating soil parameters from hyperspectral images. And my name is Jacob Ujimo. It's okay. Okay, is it better now?
Yeah, we can hear you now. We some noise in the background, but see if you can. Okay, he's not anymore there now. Okay, now he's back. It's important to make a sound check at the beginning before the session. We have another proof. Jacob? Jacob, you're muted.
Okay, can you hear me now?
Yes, we can hear you. It seems that you are in the field.
Yes, actually, I'm on the move. That's why I'm not.
I see. Okay, please go ahead with your presentation. Yeah, it's in an extreme condition. Maybe you can switch off your video. If you can switch off your video and just share your screen. I think that is going to be very much difficult to listen to this intervention, unfortunately. Let's wait a couple of more minutes, I would say, to give him the possibility of presenting. And then, yes, unfortunately, we don't have even the third participant, which did not attend. Let's wait a couple of more minutes.
Okay, can you hear me now? I'm really sorry about this.
Yes, we can hear you. If you can just please go ahead.
Okay, thank you very much. Let me share my screen. Okay, so my name is Jacob Ojumbi again. I'll be presenting on the GeoAI challenge, estimating soil parameters from hyperspectral images. So a little bit about me, I'm a data scientist who has a lot of passion for solving environmental challenges with AI. And of course, I'm very skilled with using Python and machine learning packages to create data-driven solutions and to help make business decisions. So about the background of the competition of the challenge. Now, an innovative initiative by ESA F-labs and QZ is set to transform the landscape of farming by leveraging in-orbit processing. Now, the goal of this is to help farmers to improve their agricultural practices and to encourage sustainable agricultural processes across in the world, actually. Now, the competition on Zindi, which of course Zindi is a data science competition that was used for this challenge. So we had So the primary goal was to advance soil parameter retrieval by using the hyperspectral data, and of course to use AI to solve the problem there. And now the challenge is actually focused on the estimation of the specific soil parameters, including potassium, P2O5, magnesium, and pH too. So, of course, the data consisted of about 286 patches, and that was divided into two, the training and the test set. So, 1,732 for the training and 1,154 for the testing. Now, of course, the patches, just like has been discussed earlier, the patches for this challenge were about 60 by 60 pixels. So that's where the ground truth data was estimated from. And of course, the data consisted of about 150 bands, which ranged from about 462 to 942. And then there was a difference of 3.2, that's our 3.19, approximately 3.2 between each of these bands. And so, of course, the maxed patches are the regions of interest, and that's where we're to find a solution. Now, the ground truth data was gotten from the laboratory and used in this challenge. Now, this slide is just showing an overview of how the data looks like. The first one there is the sample ground truth data. That's just showing how the data is. I mean, we have 4 different soil parameters as the potassium, phosphorus, magnesium, and pH, and we are to estimate them. And also for the band, we also have, so I said earlier that the bands range from about 460 to about 964. Now, if you look at the band, if you look at the band here, you can see that we have 462.08, 465.27. If you subtract that, that's about 3.19. And I calculated that for several of all of them, and I saw that there were about 3.19 difference and 3.2 approximately for all of them. And of course, the third one here is the third one, just representation of the band. So it's just showing the patches there for that particular one. Now, this is so I had to do a little bit of analysis to see how the data actually looks like, and I had to look at the distribution. Now, I looked at the distribution for the histogram of phosphorus, potassium, magnesium, and the pH. Now, of course, looking at this, the odd one is most likely the phosphorus. And really, when I was doing the modeling, I found that more difficult to get a very good score. But all others, they were they were close to, they had low RMSE. That's what I mean. Now, the phosphorus is not representing a normal distribution, unlike the other ones. So of course, the one that gave a very good result at the end of the day was the pH. And of course, looking at it here, it looks like a very good normal distribution. So that was just a little bit of analysis. Now for the data processing and feature engineering, I had to, so of course we have about 150 columns in the data. So I had to understand how they were gotten. Now I said earlier that the first band, for example, was 462. The next one was 465. So I was like, okay, let me, how can I relate both of them together? So I decided to find the average of them. Now, for example, I did 2 averages, 3 averages, 5 averages, and 7 and 10 averages. Now, what that means is that, for example, the first and the second band, I found the average. So that's like 1.5, like the average of those 2 values when you check the columns. Now I found the average. Same thing for 2 and 3, same thing for 3 and 4, same thing for 4 and 5. So that's what was the 2 consecutive columns. That's what I mean by that. Then for the 3 consecutive columns, I did the average of the 1, 2, 3 bands. Then the next one, that's 2, 3, 4. Next one is 3, 4, 5. So found the average of all of that and wanted to extract out more features for the data. I did that and stacked them together at the end of the day with the original data. Now I moved on to using the polynomial features in sklearn to create more features, because this was sort of a difficult challenge, because we can't just take out features out of the blues. So I had to use the polynomial features to create more features. So I used the degree of 2, and at the end of the day, I had about 36,856 columns, and that was a lot, really a lot. So I discovered that, okay, I could use the PCA to just reduce the dimension. So I went on to use PCA to reduce the dimension, and of course, the standard scaler, I used standard scaler, which performed better than all other methods, including min-max scalar and robust scalar. Now, for my modeling, I separated for the training of each of these soil parameters. I didn't just use one code. I used 4 different codes for the 4 different parameters. Now they just have little differences in terms of the models and the number of features. Now, I did a 5K-fold cross-validation because it's very important to do cross-validation so you don't overfit, you don't underfit, and all of that. So it's very, very important. And then for each of those validations, for what I did the validation, for each of those validation, I got the results and then I averaged them at the end of the day. So that's the mean. So I found the mean of those values and that was my result. And also I used the PCA. Like I said earlier, I had about 36,000 plus features, and that was a lot. So I had to reduce them between 60 to 120 because originally we were giving 150, and that was somehow a lot in a way with a few records. So I had to use 60 to 20. So I tweaked that, and I found that just around 60 to 100 was quite better than 120. So, and of course, I used the CAD Boost model, which performed better than the other model, other state-of-the-art models, including Light GBM and its gradient boosting regression. So, of course, CAD Boost was the final model that I used for my submission. That was excellent. So, the future steps, I just realized that I could spend more time in understanding the features and creating more features. Yeah, and also the train and the test data. Of course, we could bring them together and do some cross validation and ensure that it's working. It's just to learn more from it. Just to learn more from it. I wish I could have the test data to myself and to learn more in this competition. After the competition, of course. Yes, thank you very much, and sorry for the background noise. Thank you.
I thank you very much for this presentation in very difficult condition on the field, I see. So now is the time for deciding the winners. Okay. I'm seeing myself on your mobile in the field. Wow. So I will give the floor to Nicolas and Jacob, because they will need to announce the prizes, and then we will deliver the certificates accordingly, and you will also win a money prize. Okay, the floor is for you.
Let me share my screen so that I can display a little bit things. Okay, so let's announce the winner. Just to say that obviously we went through many submissions with our evaluation. It was very interesting to see the different, let's say, engineering solution that was proposed by all the participants. This is also some kind of fact that we have seen as well on our side when we organized this Hyperview challenge some months ago, is that using deep learning is not so easy on this kind of data set. And usually, machine learning and point-wise measurement and techniques was actually quite powerful. And I guess what we have today proposed by Jacob and Julius represents very well what we have seen as well when we did our competition some months ago. So with that, with no further ado, let's announce the winners. Well, I have 2 slides, but obviously when I will display the second one, the first one will know. So we decided to actually to go for the second, which is actually Julius, and the first then will be then Enigmatics and Jacobs. I think that from the information that we had, it was very hard to change the order from the, let's say, from the quantitative assessment and the leaderboard. So this is our final, let's say, ranking. So congratulations to you, Jacob and Julius. You did very great on your activities, and I think that it's well appreciated, at least on our side. So congratulations to both of you.
Yeah, very well done. Congratulations.
If you can all switch on the camera, also Jacob, we will be able to make actually a picture. Here it is. Jacob, I thank you very much. It was, I see that it was very, very difficult for you also to make the presentation in that condition in the field. So let me take actually a picture. If you can put the slide with also the rank number 1, enigmatic. I'm gonna take the picture. Okay, I have a lot of different light. Okay. So I thank you very much for being present at this event. We still have actually a few minutes, and so I'd like to mention that we had 5 competitions this year, and this one was the last event. We have already organized all of the other finals. So we'd like to know if you have any feedback about the competition from Julius and Jacob. How can we improve on this? And then I would like also to hear from Nicolas and Jacob, if you may have some other plans for organizing competition also with us, if you have some interesting projects that you can already announce. So who want to start?
And me, I can start. So
yeah.
Thank you so much for organizing this wonderful competition. What I would like to say is that ITU this year, we've been on Zindi platform for a while, and through ITU we've seen very quality competitions that really have the potential to change our current condition as a planet. So we appreciate you so much and the host you are bringing along. Like as I said at the beginning, this was the first competition I did on hyperspectral images, and it was interesting. From the explanation from Jacob and Nicolas, yeah, for me it's very interesting work they are doing, trying to see the problem in the society and trying to solve them. So maybe my suggestion for future maybe collaborations or such competition, I would say maybe it's good. Probably we can have a forum before the competition is launched, or maybe just immediately after launching. So like the host presents the problem they have, and maybe they can even see the solutions that they already have and what they are looking for. Just something to shed light on what is required in that particular competition. So that is something that can really go a long way in helping maybe improve participation. Yeah, from the data scientist community. That's all I had to say for today. Otherwise, thank you so much for the prize and every other thing. Thank you.
Thank you very much for this suggestion. We are really taking note of this, and yes, it is true that also for different other competitions we had this feedback to organize maybe one session when the competition begins in such a way to really have everyone on board. Thank you very much for the feedback. Anyone else wants to add something?
Well, on behalf of ESA and F-lab, so we were very pleased to engage with you at ITU to organize this challenge. We see that, I mean, in Europe and with the, let's say, our stakeholder at ESA, we always work with the same people, and engaging with other type of data scientists is something that is for us very, very important and very valuable. So I would be keen to really pursue this kind of initiative, because obviously data science is well, can help a little bit. I mean, we will not save the planet with data science, but at some point, I think it's spreading the word and using massively Earth observation and AI. I think it could be one direction that can help, and engaging population at large and also data scientists in the other continent, not only in Europe, but also in Africa, Southeast Asia, whatsoever, is very valuable to us. So let's continue the discussion and the collaboration, and very much appreciate it.
Excellent. I thank you very much for your feedback. Yes, it's a point that of course is very relevant for an international organization of the UN system as we are, to bring technology to all, also in developing countries. Let's keep discussing and organizing more events like this.
Definitely.
Jacob. Also, we hope that it was actually fun for you to work on the challenge, because it was also fun for us to observe you working on the challenge, and you compete. We know the data was difficult in many sense. I mean, it was very heterogeneous. It was highly dimensional, but it is still real. So I think it's fun to work on real challenges in real data to perhaps bring real impact on the planet.
Thank you very much. And before closing the event, I would like to make an announcement, because we have launched a call of paper for a special issue on geospatial AI to advance the UN SDGs in the ITU Journal on Future and Evolving Technology. Let me share the screen so that I can show this special issue. Let me open the link. Can you see my screen with the web?
Yeah, we see it.
Excellent. So it's a journal which has been already in its fifth volume, and basically it's an issue which in which the leading guest editor is Maria Brovelli, who is leading many of the GeoAI activities in the ITU. So I would like to announce that this is now available, and we accept submissions, and so an innovative approach for any of the topics which are outlined here, like application and case studies, like it could really be also the experience, learnings, and perspectives from the competition that we had. So we normally see with the participants of any competition, if they want to collaboratively make actually a paper which we can consider. So if also Nicola and Jakub, you are interested in contributing, of course your contribution will be very much welcome. And with this, I think that if we don't have any other comments, we can close actually the session. And I thank again all of the participants. Yes, I have raised the hand from Julius, please.
Yeah. Thank you so much. A while ago, there was a roundtable discussion on how to publish a paper on on these solutions you are trying to create. So I've been looking for. I didn't join the online meeting. So I was wondering whether it was recorded and maybe posted somewhere. I've been following the YouTube channel for AI for Good, and I haven't seen it yet. So possibly maybe later, or maybe if you have information right now, you can.
Okay, no, I don't have the information right now. Maybe Thomas. Okay, we will put the link on YouTube at a later stage. I see. So we will let you know when it is available on YouTube.
I'll keep checking. Thank you.
Yeah. So again, I think that if we don't have any other raised hands, we can maybe close this session. I want really to thank all the participants of this competition, the two, Julius and Jacob, which have been able to present, but then also all the many participants which have actively engaged in the competition. I want to thank again the host of the competition, Jacob from KP Lab, and Nicolas from F-lab ESA. It was very nice to organize jointly this event. I wish to remind you all that this session has been recorded and will be available shortly on YouTube and on the neural network. I think that with all of these events, not only from the GeoAI competition, but also from the GeoAI Discovery Series, which is again managed by Maria Brovelli, we are starting really to accumulate an impressive GeoAI educational material. So I encourage you to go online and see all of the recordings. And with this, I thank you very much all again, and I'll see you soon with another GeoAI event. Thank you very much. Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Mm-hmm.